and this is topic B. Again, SL, paper 1A, November 2025. Okay. Insulated solid copper rods of different diameters and fixed length are placed in thermal contact. Two objects X and Y maintained at different temperatures. Diagram shows the setup with one such rod. Okay. Which graph shows the variation with rod diameter D of the rate of change of thermal energy transfer along the rod? Okay, so we have an equation for that, right? It's equal to negative Ka delta delta T for delta X, right? And delta X is this thickness or distance, and A is the cross-sectional area. And so if we're saying the diameter of the rod is changing, then we're essentially saying it's proportional to D in what way? And what can we say? Area is equal to 2 pi r squared, right? And so if we have diameter D, that would be D over 2 squared. And so it's proportional to D squared. And so we can say that our graph should look like this, right? For every increase in D, the rate doubles. So D should be the right answer. And now we have question 7. 50 grams of liquid are heated with constant power output of 100 watts. All the power goes into the liquid. After 60 seconds, the rise in temperature is 50 K. With the specific heat capacity of the liquid, K. So we have power. Power is equal to 100. And we have, and so power is, and we have Q over T, right? That is what gives power. Power is Q over T. And so Q is simply M 0.08 C times T 50K, and we are told that after 60 seconds. So how long is that? And so we have 60,000 divided by 0.08 times 50 is equal to what? And we get 6,000 divided by 0.08 divided by 50. 1500, and that's our answer. The energy balance model of a planet's climate is shown. The reflected and radiated intensities are given in terms. So these intensities are given in terms of the incident incoming intensity I. Okay. So with these diagrams, it's a energy balance model, right? So everything has to balance. Let's read the question. Radiated intensity from the surface of the planet. Okay. So we're trying to find this. And so what we know is that everything coming in should be going out of the same layer. So everything coming into the atmosphere, that is I, should also be going out of the atmosphere. And so that's why we have this 0.25 plus 0.15 plus x, right? This is something we need to find as well. And that is equal to 1. So what is x? X is, so 0.41 minus 0.4 is equal to 0.6. And so this is 0.6i, right? And now we know 0.1 is emitted back down. So that means the total radiated from the surface of the planet is 0.6i plus 0.1, which is just 0.7i. And so our answer is C. And the other way, another thing we can talk about is what is going into the planet's surface and what is going out of the planet's surface. So we have 0.15 going out of the planet's surface, and we have this 0.7 going out of the planet's surface, and that becomes 0.8, right? 0.85. 0.15 plus 0.7 is equal to 0.85. And so how much is coming into the planet's surface? We have 0.1, and so that means we have 0.75 I here, right? They didn't give us that diagram, like how much is crossing the atmosphere and ending up on Earth and absorbed by Earth. So that's absorbed, right? So everything balances out, because now we have 0.75 plus 0.1 is equal to 0.85 as well. So whatever comes into the Earth's surface also goes out of the Earth's surface. And whatever comes into the atmosphere also has to go out of the atmosphere. And the same can be said about what goes into space and out of space, which is what we did up here. So number 9. A rigid vessel of volume V contains n molecules of an ideal gas. The average kinetic energy of the molecules is Ek. What is the pressure in the vessel? So average kinetic energy means Ek per molecule, right? So per molecule, that's the average. And so per molecule, right? And okay, now we're trying to find the pressure. So pressure PV is equal to NAT. But we also know that the internal energy is also equal to the kinetic energy for an ideal gas, right? Because there's no intermolecular forces. So there's no potential energy between molecules. And that is equal to 3 over 2 NKBT. And so what we can do here is substitute. And so we have Ek is equal to, and remember this is per molecule. So we have 3 over 2 NKB. So substitute that, and we have PV. So pressure is equal to pressure per molecule is equal to 2 Ek over 3 V, right? And that's the volume. But we need to multiply by the number of molecules. So P total in the vessel is equal to 2Ek and 3V. And our answer is B. So next one. A substance changes from liquid into solid without a change in temperature. Without change in temperature. And what is true about the internal energy of the substance and the total intermolecular potential energy when the phase change occurs? Okay, so during a phase change, there is only a change in intermolecular potential energy, not in kinetic energy. No change, right? So when we're going from liquid to solid, these particles, which are slightly apart, then become closely packed, right? Tightly packed. And so we have a decrease in the intermolecular potential because now they're closer together and there's no sort of restoring potential, right? Restoring force. And so intermolecular decreases and the internal energy decreases with it, right? Because internal energy is Ke plus potential energy. And so our answer is A. 11. In the circuit shown, the cell has negligible internal resistance. Which equation is correct? Okay, let's look at this. So most of these are writing. Okay, so we have to write the currents in terms of each other. So we have 3R here and R here. And this is a parallel circuit, right? And so what happens here is it splits. Now, how much is allocated to each? Let's say we have 4 here, and like our total resistance is 4R, right? Not the total resistance of the circuit, but in terms of how many resistors we have. And so if we have 4, 1 amp would go here, and 3 amps would go into that parallel circuit. And so, and that's because of our formula, right? V is equal to IR, when voltage is the same across both, right? Across both parallel circuits. And so, if R is greater, then I is smaller. So, and it's proportional, right? If I make R 3 times smaller, I has to become I nu, let's say, has to become 3 times bigger. And so that's how we got that. Okay. And so what we can now say is I3 is equal to 4. Okay, let's look at this. This is definitely not true because I1 should be equal to I2 plus I3. That's the most important rule. And then we have this, and that is perfectly true, right? We have I1 is here, is equal to 4 times I2, which is just 1. I1 is equal to 4. And so this one's true. Our answer is B. And that is it for topic B.